joined ISA Thiruvananthapuram, and later he moved to Indian Association of Cultivation of Science, Kolkata. His research spans wide range of cutting-edge topics, from exploring two-dimensional materials, their solvent phase exfoliation, and uncovering mechanism in catalysis, quantum mechanical tunneling, optoelectronic properties of organic molecules, and their dynamic behavior. His work has resulted in 200 publications and hold an impressive H-index of 46. It's no surprise that he ranks within the 2% of scientists in chemical physics globally, as recognized by Stanford University. His extensive list of achievements include SERB Distinguished Investigator Award 2019, BM Prize in 2017, and recognition as Young Scientist by Indian National Science Academy. He has also served as the Associate Editor of Bulletin of Material Science and also a member of editorial board of Journal of Physical Chemistry. With that, I invite Professor Ayan Datta to handle the first session.
First of all, let me start by thanking Professor Pradeep for the wonderful invitation. Well, I must admit that I know that Professor Pradeep arranges this outreach activity for this particular college, and this is actually a very nice scientific program, and I have heard. And as soon as I got the mail, so let me give you a scoop, first of all. There was an invitation there was a conference in IIT Guwahati running exactly at the same time, and I had accepted that, but as soon as I got this invitation from Farook College, I politely said that I have a stomach upset and sorry, I am not going there, I am coming here. And the reason is very simple. Of the standards with Pradeep and the standards it maintained. Now that is not only of the academic, because I'm sorry I had to come, I had an exam duty, so I had to come I came only yesterday late night, and then I could see the kind of passionate interactions with the student. I think this is the way to make the small steps, and as Steve Jobs would say, connecting the dots. So when you connect the dots, you don't realize what is the path you make. But I'm sure Professor Pradeep is going to make a wonderful path. Now, this lecture is also going to be special because the person who is chairing the session also happens to be my first PhD student. So I have to be very careful, and I would always request her not to cut me off in between my lecture. So the point which I'm going to try to make here is, we all know graphene, and graphene has been talked a lot about. But this is just to make a point that if you are a chemist, the molecule of interest would be benzene, and then if you fuse benzenes together in a same plane, experimentally it is easier said than done. You cannot fuse benzene molecules like this. But then, if you are able to actually tie several benzene molecules like benzene, naphthalene, anthracene, tetracene, polyaromatic hydrocarbons, all the molecules which give you cancer, right? And if you make bigger and bigger molecules like this, and there are groups in Germany which actually try to make polyaromatic hydrocarbons. You can make benzene molecules. I mean, you can fuse hundreds of benzene molecules together as a single molecule. These are like massive, what I would call as graphene fakes. You would be probably making a chemical equivalent of graphene. And then, depending on the way you fold graphene, you would be able to make nanotubes of various chirality. And this is something which we asked. Now, the question which we've always wanted to ask, and this is a question which the students will also ask, is that why do we always work with carbon-based material when we talk about graphene? And the reason is, I mean, this is also counterintuitive, because if you think of it, most of the microelectronics, whichever you are using in your mobile phones and computers, are based on silicon. So the question which we wanted to ask at this point of time, this is about 10-15 years back, is how can you make, or why there is no graphene in our equivalent of silicon. And what do we call it? Well, we chemists would call it silicene, because like graphene, you have two-dimensional graphene fused into benzene. You will have two-dimensional carbon, two-dimensional silicon, which would be fused into silicenes. And now, as it turns out, the issue is simpler. Issue is more complicated, because as you know, in carbon, there are two pz orbitals which are standing like this, perpendicular to the plane. Now in silicon, there are little bigger, more diffused 3pz orbitals. And we already know that 3pz orbitals, being too big and too diffuse, do not have so good a pi bond as that of carbon. So there is a strong trade-off between the sigma and pi orbitals. and this is something which affects the planarity. Now the question here, and this is particularly for the students, look at the title of the paper. This is very important. In fact, I would say this is one of the first paper, by the way, this is also a theoretical paper. Look at the year, this is 1994, and this is from the group, this is from Japan, Shiriashi, and the title says Theoretical Possibility of Stage Corrugated Silicon and Germanium Analogues of Graphite. Today, if you write this paper, everything else will be the same, and you will call it graphene. The reason why you call that thing graphite, because in 1994 people actually did not know that you could peel off layers of graphene out of graphite. And how do you peel off? And it is the smartness of Novoselov and Gaim who could actually peel off layers of graphite out of graphene. You see, I don't know, but what do you call it in Malayali? See, there is whenever during summer, when you have your mango pulps, and then you make layers of mango pulps and store it, and they come out as layers, as exfoliated layers. You have something in Malayali of equivalent? Well, in Bengali, okay. So we have layers of those things coming out. I did not train her well in Malayali, of course. Okay. So in any case, so these are layers of graphene. So exactly graphene comes out like this. Those layers of, like those mango, very thin wafers of which comes out. So the point is, this is very important. In other words, it's not the point which I'm trying to make. The point which I'm trying to make here is, you have to be relevant. So what was graphite in 1994 would qualify as graphene today, because now experimentally you could take out few layers of graphene out of graphite. You could just peel off. And of course the students know the answer why you can peel off layers of graphite out of graphene. The answer is, in graphite there are layers which are packed of graphenes which are packed, but they are packed by only weak van der Waals interactions. There is very strong covalent interactions in the plane and very weak non-covalent interactions. So those weak non-covalent interactions can be peeled off like an adhesive tape. Understood? And there have been other examples of this. Now the field of course took up with this article in Physical Review Letters, where they said that you could make two-dimensional silicon like that of graphene. Now, incidentally, we are chemists. So we started by asking a very, very simple question. And this was, I just became a faculty at the time. So we asked a question, how many carbon atoms in benzene can be replaced by silicon and still the ring can be planar? So look at this molecule. Now this is naphthalene, in which one of the carbon atoms has been replaced by silicon. This is benzene, in which one of the carbon atom has been replaced by silicon. The important thing to notice here is both naphthalene and silicon and graphene or benzene have remained planar. So the point which I am trying to make here, experimentally, these are experimentally known that you could replace one carbon atom from benzene by silicon and still the system remains planar. Now there is a condition. Being experimentalist, you will see that you cannot replace one carbon by silicon just like that. You have to have these very big bulky groups. Why you need this very big bulky group? Because a carbon-silicon bond is very, very prone to oxidation. So you have to give very big protecting groups across the system to protect it from oxidation. Now the question here as a theoretician would be, the fact that I could see that you could replace one carbon by silicon and still remain planar, is it an effect of that group? Or is it a genuine effect of the replacement of carbon? Well, this is the question which you wanted to ask initially, and that is the question which we asked. So I had a bachelor student, BSc first year student from Kerala who had visited me for a summer project, and then we said, okay, we'll do a very simple toy experiment. And the toy experiment is we replace carbon and then we see how many carbon atoms in benzene could be replaced and to get what we call as hexacillabenzene. Remember, this is 2010, none of these molecules were known. None of this was known. So then this was hexacillabenzene, and this molecule, what we predicted was puckered. The planarity is lost. And gratifying for us, 2010 itself, Seskevich reported this synthesis of hexacillabenzene in Science, and exactly as we predicted, the structure was bent. And of course, you can see that for experimental conditions, you really need those protecting groups, but then the basic interaction still remains the same. That, in other words, puckering is an independent phenomena of the system, and in other words, having carbon replaced by silicon does something to its chemistry which is probably independent of the modes of synthesis. There is something more fundamental into it, and that is something which we have been looking at. The other very important thing I would say, because Professor Pradeep is also here, see, this is 2010, and it took us several months to do it. Today, if we do it, it will take an afternoon. The point which I am trying to tell you, things which were important, which were good, they were good, important at that point of time. Today, if you want to be competitive, today you want to be compete with China, today you want to compete with Germany, we cannot be going and sticking to something 15 years back. In other words, now for people like you, you have to be on the right bandwagon. So it would be a criminal injustice that if you ride a bus and that bus travels at 10 kilometers per hour. The world is running at 200 kilometers per hour. In other words, be very clever, choose the correct opportunities and make the right decisions. That is what is important. Okay. We also found that at a point of time, if you had a perfectly planar graphene equivalent of silicon, that would be buckled, and it is the buckled structure of silicene that is the stable. I'm sorry that I don't have I would not have time to explain what does this mean, but if some of you are interested, these are what are called vibrational instabilities. If you want, we can discuss about it. The point which I'm trying to, the take-home message till now is graphene is perfectly flat, silicene is buckled. And then we'll try to understand why silicene is buckled while graphene is flat. That is the point which we are trying to learn today. Interestingly, at that point of time, we also learned that if you could replace the benzene by, the silicene rings by lithium atoms on the top and bottom, suddenly the system has become planar. Now we need to explain this. So we have to explain two phenomena. You replace carbon by silicon, the perfectly planar benzene becomes buckled. Now on the top of the buckled silicene, if you put lithium or anything which gives electrons to it, it again regains its planarity. So how do we reconcile with these two phenomena? That is the point which we are trying to make. Again a point, again a caveat. At that point of time, when Deepthi was in my group, we of course published it and did whatever. We never knew that nature actually had a phase of silicene, but not in lithium, but in calcium. And this is the phase of calcium silicide in which there is perfectly planar silicene, in which there are calcium atoms which are intercalated between the rings. Now the point is, why did we do lithium instead of calcium? The answer was, we wanted the calculations to be a little faster. Now the point again to make is, it's good to take shortcuts, but it is also very important to realize what approximations we are making. At that point of time, had we really known that there was a calcium silicide experiment, then we could have made a much bigger impact. The point is also that when we have papers, particularly I'm telling to myself, theoreticians, well, we are very good, we are all very good in our own local minimas. Only when you talk to experimentalists, you get corrections. Other than an experimentalist, nobody will tell you that instead of lithium, you do calcium. That information we never had when we had the theory paper. That is the point which I'm trying to make. It's very important to collaborate. That being in their individual, buckets, or what as people now call in silos, we can do things, we can be good, we can be happy, but that will have no impact, low impact. And this is something I learned from my own experience. So I only tell from my own experience. Now, how do we explain this? As it turns out, this is known for the last 60 years. And this is a theory of vibronic interactions. I will tell you the theory. It's a very simple theory, and I will explain to you why. Consider every molecule would have a ground state and multiple excited states. Well, the molecule can also have multiple ground states. Molecules, what kind of molecules have multiple ground state? Molecules which are open shell molecules, like which have unpaired electrons. They generally have multiple ground states. But in case this molecule is closed shell, there is a one ground state, and there is going to be an excited state. Mostly there are multiple excited states, but we will take a very simple model, which model is called two-state model. One ground state, one excited state. Now the ground state and the excited state can interact among themselves. How do they interact among themselves? They interact among themselves by what we call as vibronic interactions. And what is the effect of vibronic interactions? The ground state becomes more and more relaxed, and the excited state becomes more and more rigid. Now this has been known from 1950s when Hertzberg and Taylor were actually looking at the vibrational spectra of small molecules. And they found that when the excited state of benzene, because of vibronic interaction, actually became rigid, whereas the ground state become little relaxed. So if the interaction is sufficiently strong, the ground state will eventually will no longer be stable here, and it will develop a double minima, whereas the excited state will become more and more rigid. Now this is a direct consequence of what we known as time independent perturbation theory. If you have time independent perturbation theory, the ground state develops a double minima, and the excited, so in other words, the ground state will become vibrationally unstable. How do you verify? See, if this F square is what is called the vibronic coupling constant, and if this term exceeds this one, this force constant will become negative. And what is force constant? You know, the stretching frequency of a diatomic molecule is 1 by 2 pi square root of k by mu. If k is negative, then what will happen to the stretching frequency? It will become imaginary. Imaginary means unstable, right? That is the point which we are trying to make. Now, so this is exactly what happens. In carbon, or for example in silicon, see, there is a coupling between the ground state and the excited state, and because of this coupling interaction, the ground state develops an instability. Now, when you put lithium atoms on the top and bottom, the gaps increases. And because of the gaps increases, they no longer perturb each other, and as a result, it regains its planarity. This is what we predicted at that moment of time. What happens? So look, now in that case, you should also argue, in that case, what happens to benzene or graphene? Well, problem in graphene is, or problem is, the only excited state which can in principle interact with the ground state is at 8 electron volt, very high, very far separated. And you know from your molecular orbital theory or perturbation theory, states which are far away do not couple with each other. In other words, for graphene, the layers are here, but when you go to silicene, the levels are much closer, then they vibronically interact and cause what we call as second order Ayan-Taylor distortion, or what we call as pseudo Ayan-Taylor distortion, right? Now look at what silicene, the gaps are much smaller, and because of much smaller, it has developed an instability. So we also did further calculations at that moment of time. By the way, this is about 2014, silicene was not discovered, silicene was known. So we predicted that same thing, if germanine would be discovered, germanine would also be buckled. This is 2014. And then, in fact, myself and Dr. Deepti Jose, we wrote an article in Accounts of Chemical Research, and we said silicene is going to be very, very different from graphene. This is 2014, nothing much was known. Incidentally, luckily, then we started seeing 2015 onwards, there was a plethora of literature where people are saying buckled germanine. Why buckled? Because we had predicted that germanine, also the layers are close to each other, and then they will get buckled. And because of buckling, that's what the predictions which were made. And there were a lot of, in fact, in the last 9 to 10 years, there will be at least 10,000 papers on germanine. And when all of them have invariably found germanine to be buckled. Invariably. At that moment of time, I think this was like riding a tiger. So once you ride a tiger, you really don't know whether you will come down or not. And anyway, you are going to be marked. So at that point of time, there was another 2D system which was discovered, which was called phosphorine. What is phosphorine? It is two-dimensional phosphorus. And when phosphorine was discovered, interestingly, and by the way, I will come back to phosphorine, it also helps us understand that why the structure of silicon. Because if you have a two-dimensional silicene, they will couple with each other as layers, because those atoms are coming and it will form a bulk structure of silicon, and this is the structure which you all know. This is the structure of diamond. This is the structure of diamond, right? Interestingly, this is also something to do with the way we teach things. Phosphorus, in fact, if you open your any inorganic chemistry textbook, phosphorus has several allotropes, many allotropes. The most common allotrope is white phosphorus. Where do you use white phosphorus for? Any idea? During Diwali, those colors, right? It also has red phosphorus, violet phosphorus. Interestingly, among all the phases of phosphorus, the most stable phase of phosphorus is called black phosphorus, which is a layered material. But this is also puckered. But look at the structure, this is puckered in a little different way. This is puckered like this. It has a stapler clip-like structure. Whereas there is another form of phosphorus, which is called blue phosphorus, which has a puckering like this. more like silicene. Now, the other important thing is this is also something to do with, see, when we say phosphorescence, you have used the word phosphorescence, right? See, phosphorescence has the use of the word phosphorus, but it has nothing to do with phosphorus. Is actually nothing to. The reason why phosphorus gives a color is not because of phosphorus, but it is actually fluorescence from those phosphorus oxide particles, right? Now, at this moment of time, the smarter students would have already realized. Now, you see, phosphorus has distortions, but it has two different types of distortions. And if it has two different types of distortions, two different structures, then there will be two different vibronic interactions which is going to create this. In other words, by the way, there is a lot of literature on phosphorines, massive literature. And you see, this is the structure of black phosphorus, this is the structure of blue phosphorus, and they differ. And because of the nature of the buckling is different, their properties are also different. Black phosphorus is a direct band gap material, blue phosphorus is an indirect band gap material. More importantly, black phosphorus is probably, even, I think today if you ask me which is the most important 2D material in electronic sense, it is black phosphorus, because black phosphorus has a natural band gap of about 1.5 electron volt. Very important, that gap. Graphene doesn't have a gap. So you have to dope, you have to give electric field, you have to do a lot of work to create the gap. This system is already made with the gap. Well, as you know, in life, nothing comes for free. Black phosphorus has a gap, but black phosphorus is also sensitive towards oxygen. So typically its shelf life is about 3 to 4 months. So there is a trade-off between the two. So what we said at that moment of time, that you have if in case we have a hypothetical perfectly planar phosphorine that can undergo distortions in two different ways, and those two different ways is like one will create black phosphorus, another will create blue phosphorine, and this is exactly what we found. A distortions along the B2G vibrational mode will give you blue phosphorine, whereas the E1G mode of distortion will give you black phosphorine. And both of them have vibronic interactions, mixing of the ground state with an excited state, which does this magic. Now, there is a very important point. In other words, what we are trying to see is that the distortions of two-dimensional systems happens because of vibronic interactions, and because of vibronic interactions, many of the two-dimensional systems other than graphene or probably hexagonal bononitride are going to be buckled, and that is the predictions which we had made, which are in agreement. By the way, this also leads to important consequences. The consequences, as see, the exposed surfaces are different. So since the exposed surfaces are different, one of them acts as a P-type diode, another acts as an N-type diode, because the amount of charge transfer it is giving is different. Now, there is a problem, and the smarter student should ask me, any molecule, any material has a very large number of excited states. Now, if there are a very large number of excited states, there will be always some excited state which can interact with the ground state to create this instability. How do I know which is the more important state? Now, the question is, well, I can always do computation. Now, if I do computation brute force without talking to an experimentalist, I will tell you what it happens. So, let us assume I am that kind of a proverbial horse which knows very good computation, but close our eye and only does calculations. So, what I will get is a result like this. I will find that there are 13 excited or 17 excited states which can interact. So, I will get an obnoxious number which will have no chemical physical meaning. No experimentalist would be interested to even talk to me. It has no meaning. It has only numbers. But numbers are not important. It is the physical insights which is important. Now, what we did at that moment of time, we were able to actually decipher the most important interactions. And what is this interaction in a chemical sense? Think of it. It is an interaction between a filled orbital and an empty orbital. Well, in chemistry, there is a word for that. That word interaction is called hyperconjugation. Hyperconjugation is exactly that. Interaction of a filled molecular orbital with an empty orbital. In other words, what we did, we were able to find out the important hyperconjugative interactions, and eventually when we found that there are only 2-3 interactions, and all of them are sigma pi star type interactions. Where do you get okay, now the question is, where do you get to see this kind of sigma star, pi star interactions? Well, if you are doing spectroscopy, you get those interactions. Sigma star transitions, pi star transitions, n pi star transitions, n sigma star transitions. These are exactly like them. These are like transitions from the filled orbital to the empty orbitals. And this is exactly what we found at that moment of time. And in other words, we were able to find out very simple qualitative tools which can help you understand why a two-dimensional material is going to be distorted. At that moment of time, there is also a lot of interest in other forms of graphene. For example, look at this structure. This structure is called T-graphene. Why is it called T-graphene? Look at this structure. This is called tetragraphene because there are 4-membered rings which are connected, and they are connected to form structure like this. There is also something called trigraphene, in which you see it forms octagons, and then there are those triangular units. Interestingly, these network systems have a very interesting property, and the most interesting property which arises because of their buckled structure is when you heat them, they contract. Now, this is something which is very, very counterintuitive. When you heat any material, most materials expand. Most materials expand because the coefficient of thermal expansion of most material is positive. Well, the students will immediately argue, well, sir, the molecule of life actually does something very critical. The molecule of life, water, actually contracts in a very small temperature zone between 0 and 4 degrees centigrade. And you know that, right? So, between 0 and 4 degrees centigrade, water actually, or in other words, ice, actually contracts if you heat little between 0 to 4 degrees centigrade. And you will say, sir, this is a very small range. Well, nature does a lot of effect with that. All the Arctic fishes survive only because of this, that as soon as the temperature falls below around 0 to 4, the top layer of all the Arctic Ocean and the Antarctic Ocean freezes, whereas the bottom remains a liquid, so all the fishes survive in the bottom. Now, well, nature is nature, but we are material scientists, we want to do some things which can do much better than nature. For example, these systems, trigraphene and T-graphene, they have coefficient of thermal expansion which are negative till 4000 Kelvin. In other words, you can take the material, start heating them, and the materials will start to contract. Where do you use it? Well, you will immediately realize the first place where you use negative thermal expansion. Okay, I give you a data. I mean, I'm sure the young people will never have this problem, but your parents will have that problem, and I'm started having that problem. See, maybe in Calicut you don't realize because the weather is so optimal. See, if you're in Delhi or somewhere, you will see that when it is very cold or it is very hot, you have toothache. It's a very common problem. See, what happens when you have typically when you have root filling, the filling material needs to have zero coefficient of thermal expansion. Otherwise, either it is very hot or very cold, your filling will change. As a result, people actually have a lot of trouble in their teeth. So there is a very important materials like this, materials for negative thermal expansion, or at least zero thermal expansion. So what we have predicted, and this was in last year, that we showed that this kind of two-dimensional materials with buckling are excellent in having negative thermal expansion. They actually contract on heating. Now, the question is, I have not told you why they contract on heating, and I'm going to explain to you why in the next 1 minute. So, see, the reason why they contract on heating, they are called what are called rigid unit modes. There are those simple modes, they actually change their dihedral angles, and in a way, look at this structure. When you heat, this individual tetrahedras move, and you see the end-to-end distances changes. And as a result, the end-to-end distances contract. As a result, the system becomes, instead of expansion, it contracts. So, right? Now, before I go to the last example which I wanted to show you, this is also something which I want. See, why these materials are very strange with buckling these two-dimensional materials? See, when you heat something, all bonds contract. When you have an atom, two atoms connected by a bond, they contract. But remember, chemistry is not only bonds. Chemistry is also angles and dihedras. So, when you heat them up, some of the dihedral angles actually undergo this kind of a motion. So, if my end-to-end distance is this, when you heat it up, it becomes like this. Now, if you actually measure the end-to-end distance, this is shorter than this. So, as a result, my system has contracted. Last year, we were also able to, in collaboration with an experimental group, we were able to show that molybdenum, which is a two-dimensional form of molybdenum, which is again going to be buckled, and just like our predictions, it was reported in Nature Nanotechnology, that we could see that the structure is buckled because of the same reason that the buckled structure, the planar structure is vibrationally unstable. So finally, I will stop here, and before I go to, I don't need to give other examples. The point is, this is the periodic table of element. And I will tell you, the atoms which are marked here are the ones for which we have known report of two-dimensional materials. Other ones are all empty. And our predictions at this moment of time is that many of the elements, if they are able to, you are able to discover or you are able to synthesize, they are going to be buckled. The reason why they are going to be buckled because they have very small homolumo gaps, and because of the small homolumo gaps, well, these are predictions, and we will like to see experimentalists actually look at those predictions and make interesting observations, either to prove or disprove our theory. Finally, I would probably end up by saying, see, when two-dimensional materials were discovered, everybody wanted to make pure, defect-free, perfectly planar, perfectly hexagonal two-dimensional material. But now we have realized that only with defects, buckle, controlled defects, you get real properties. So I think this is the tagline of Surf Excel, which used to say, "Daag achhe hain." It is good to have defects because that adds a lot of chemical value to the system. And finally, I would also like request you that you can consider. I'm going to just be an associate editor for ACS Applied Energy Materials, which is a reasonably good journal for the energy portfolio things. And Dr. Kanishka Bishwas is a deputy editor from India. And so you can send some of your good papers to this journal, and I'm sure that you would get a kind of a fair judgment from the editors as well as the other members. Thank you.
Yes. Now the session is open for discussion.
What can I tell you? It's a fabulous journey through 2D materials. I was particularly impressed by the way the teaching style of the presentation made it magical. Thank you.
And you know, sir, your appreciation means a lot to me. Thank you very much.
Thank you. Very nice. Very nice. So I was thinking about this lithium in silicon or 2D silicene systems. There is a person called EQE, who has been looking at silicon as a material for lithium cells. So I wanted to know, what is your thought on your work and relations to electrode material?
Yes, sir. Actually, we had also looked at anode materials based on, they were trying to replace graphene by silicene as anode materials. The problem again with silicon is the two-dimensional silicon is very air sensitive. So it reacts with atmospheric oxygen.
Yes.
So, I mean, even though the kind of, the theoretical specific heat or the capacity, the lithium, I mean, the storage capacity is better for silicon, the problem is some of those oxidations becomes a problem. So if there is some way to control that oxidation or put it in an ionic liquid which protects it from aerial oxidation, I think that can be a good one. In that way, that is my initial thought on that.
The other related thing to expand on that was that silicon is said to be, or such sheets are said to be new materials for capacitive deionization of water, desalination of water. So the way you said lithium, calcium, and several things that go in, is it likely that it can be a universal scavenger addressing the capacitive deionization problem?
I think that's a wonderful, I mean, I have not looked at it in any literature, but I'm sure one should look at it. I think because, see, the other very important is silicon, those minerals are going to be very stable. So some things which you have been able to remove, deionize, is going to be stable for a very long time. The other issue of things coming out and leaching will not be there. So I think this can be a wonderful material, sir. Thank you.
Sustainability and such other issues. Yeah.
Yes.
Thank you.
Thank you, sir.
Very nice work, Ayan. I hope I get a chance to work with you.
Oh, thank you.
I learned so many things.
Thank you, John.
I had one question about if we shine light, and then do you expect that vibronic coupling will increase, and as a consequence will have a larger John-Taylor distortion?
Yes, there are spectroscopies to that. This is called optical control of vibronic effects. there are a lot of effect, optical control of vibronic interactions. There is a lot of effect in the molecular world. See, the problem is that language between molecule and materials have not yet touched. So I think there's a very good way of looking at it. Basically, where you shine light and you see the structural distortions under. And so actually the way to understand is under light you have effect of Stark effect. I mean, if you look at general, and those Stark effects, how those electronic interactions will change.
And as a consequence, will the absorption coefficients also improve?
Yes, people look at those things. That's a wonderful way of looking at it. Thank you.
Okay. The second question is when you show the distortion, that when you go to silicon and the minima has distorted, so you have to bimodal energy plot. So how does it connect it to the distortion of the ring?
Well, the question is the ring also the ring get puckered. So in other words, if you think of it, it's a perfectly planar benzene. Now, because of the distortion, 3 atoms go up, 3 atoms go down. So the structure become like cyclohexane type. Cyclohexane, not cyclohexane, but cyclohexane type.
Wonderful session. So, I'm just asking, to be frank, I haven't heard about these molybdenum. Like, I've only heard about graphene only. Then, is there any basic condition for this molecule this atom should have these conditions to form this type of molecules?
So the question is, of course, the basic condition is still the laws of thermodynamics which you have studied in your bachelor's. So anything which has to be stable under the first law, second law and third law, which effectively boils down that the free energy of the formation has to be negative. That is the thermodynamic condition. But you know, in chemistry, we are not only about thermodynamics, it is also about kinetics. So the kinetics is the free energy of activation of that system getting converted to something else has to be high. Otherwise, it will go and cross the barrier. So the condition that many of the systems have been formed and some of them have not been formed is because the free energy of activation is low. In other words, they are kinetically unstable with respect to other structures. So if something is thermodynamically and kinetically stable, I think jolly good one should be able to make some of those systems.
Thank you, sir. Thank you, sir.
So if you have no more question, please join me in thanking Professor Datta for this wonderful session. And so please accept our token of love and gratitude from the organizers.